All right, so you want to be an electrical engineer. Let's dive deep into RoleCatcher's resources and get you ready for that interview.
Yeah, there's so much to cover, but don't worry, we'll help you break it all down.
That's right. We're talking smart grids, renewable energy, all the cool stuff shaping our future. But first things first, let's nail that interview.
Absolutely. RoleCatcher's got a pretty solid definition of an electrical engineer.
Yeah, they say it's about designing and implementing electrical systems for a connected world, which is pretty spot on.
But it's not just the big power stations,
Yeah.
right?
Think about it. We're surrounded by electrical systems, even in everyday appliances that make our lives so much easier.
Exactly. So when you're prepping for your interview, think big picture. Let's jump into some of those sample questions RoleCatcher gives us. The first one is a classic.
Yeah.
Describe your experience with electrical design software.
Oh, this is where they want to see if you know your tools, right?
Exactly. AutoCAD, SolidWorks, MATLAB. Those are some big ones RoleCatcher mentions.
Right.
But there are others out there too. What software have you used? And think about specific projects, where you really put those design skills to the test.
Yeah, like, did you ever design some crazy complex circuit layout in AutoCAD?
Or maybe you ran simulations on a whole power system in MATLAB.
Exactly. And don't forget, be specific. Mention those software versions you used, and be ready to talk about the features that were relevant to your work.
Oh yeah, they might even ask you to compare different software, the pros and cons of each.
Good point. Now, what if you haven't had much experience with some of these programs?
Well, don't sweat it. Just highlight your eagerness to learn. Did you take any relevant courses, work on any personal projects to boost your skills?
Even tinkering with Arduino or Raspberry Pi, that shows initiative.
Absolutely. Okay, next question. What is your experience with PLC programming? I remember those things being a real challenge in college.
Yeah, PLCs.
Complex, but fascinating. They're the brains behind automation, controlling everything from traffic lights to entire factory lines.
That's a good way to put it.
So think about projects where you had to program a sequence, handle inputs and outputs.
Right.
Maybe you even had to troubleshoot those tricky logic errors.
Yeah.
Did you ever crack a particularly tough programming challenge? That's a story worth telling.
Absolutely. And even if you're not a PLC expert, showing that you're eager to learn and have some exposure to industrial automation, that goes a long way.
Totally. Now, this next one is all about safety. How do you ensure compliance with electrical safety regulations in your designs? This is critical. You absolutely have to nail this one.
No messing around with safety. RoleCatcher's got a good point about those regulations. NFPA 70E, OSHA, all that.
Right, you got to know the codes inside and out. But it's not just about memorizing them.
Right.
Interviewers want to see that safety is embedded in your entire design process from the very beginning.
Like, how do you anticipate potential hazards? How do you build in safeguards from the get-go?
Exactly. And how do you make sure your designs meet those top-tier safety standards?
Think about specific projects where safety was a primary concern. Maybe you had to select components with specific safety ratings or design a system with backup safety features.
Oh, and be ready to talk about how you stay up to date on those ever-changing safety regulations.
Yeah, like, are you attending workshops, reading industry publications? Showing that proactive mindset is key.
Absolutely. Okay, let's move on to a question that lets you tell a story. Describe a time when you had to troubleshoot and resolve an electrical issue.
Ooh, everyone loves a good problem-solving story.
This is where you get to shine. Pick a story that highlights your technical skills, ain't how you think.
So walk them through it step by step.
What were the symptoms? What tools did you use to diagnose the problem?
Did you have to get creative? And most importantly, how did you fix it?
And what did you learn from that whole experience? Did it change the way you approach problem solving?
Great points. And remember, tailor that story to the specific job you're applying for.
Oh yeah, for sure. If it's a power systems job, talk about a time you troubleshooted a grid outage. If it's more design-focused, maybe you fixed a tricky issue on a circuit board.
This is where those AI tools from RoleCatcher can really come in handy.
I was just thinking that.
You can practice your story with the AI and get feedback on how you deliver it. It can even analyze your tone, your body language, all that to help you project that confidence.
It's like having a mock interview with an expert who can help you fine-tune your story for maximum impact.
Exactly. Okay, ready for another technical one. What is your experience with electrical testing and measurement equipment?
Multimeters, oscilloscopes, clamp meters, they're all essential in the electrical engineer's toolkit. So think about the equipment you've used and how you've used it in real-world projects. Have you ever used an oscilloscope to troubleshoot A faulty circuit, for example.
Or maybe you used a clamp meter to measure current in a live circuit.
Exactly. Think about those hands-on experiences. Now, be honest about your experience level. If you're not familiar with a particular piece of equipment, that's okay. Just express that you're eager to learn. The important thing is to show that you understand the basics of electrical testing and how to apply them.
And don't forget those details about calibration and accuracy. Mentioning those things shows that you pay attention to detail and you're all about getting reliable results.
Absolutely. Now, let's step back and take a broader view. What is your experience with electrical power distribution systems? Here, you can demonstrate your big picture understanding of how electricity gets from the source to the consumer.
This is a big one. Think about all those different types of distribution systems. Radial, loop, mesh. What are the pros and cons of each? Have you worked on projects involving transformers, substations, or protective relays?
And don't forget, the energy landscape is changing. We're moving towards those renewable energy sources.
Yeah, how do you see that impacting the design and operation of power distribution systems?
This is your chance to show them that you're not stuck in the past. You're thinking about the future of the field and how you can contribute to it.
Right. And don't forget, RoleCatcher has tons of resources on power systems and renewable energy. Their career guides can really give you a good grasp of the latest industry trends and those in-demand skills.
Now, here's a question all about continuous learning. How do you stay current with advances in electrical engineering technology? This is where you let your passion shine through.
Talk about those conferences you attend, the publications you read, the online courses you take, even personal projects you pursue.
Be specific. Mention those journals, conferences, or online platforms that you find valuable. What emerging technologies are you excited about?
This is also a great time to showcase any certifications you hold or professional organizations you belong to. It shows you're invested in your career growth and want to be at the forefront of the field.
Absolutely. Now, let's tackle a question that often trips people up. Describe your experience with electrical system integration.
It sounds simple enough, but it can be tough to really articulate what it means.
Yeah, they're basically asking, can you bring all these different components together and create a seamless, functioning system?
That's it. So think about projects where you had to integrate multiple systems, power, lighting, control, communication, the whole works.
Did you run into any compatibility issues? Did you have to develop custom interfaces? What about making sure the whole system met specific performance requirements?
This is where your problem-solving A&D collaboration skills come into play. Highlight those challenges you faced and how you overcame them.
Oh, and don't underestimate the importance of documentation. Mentioning your experience with creating system diagrams, writing those test procedures, or even developing training materials. It all shows you understand how crucial clear communication is in these complex engineering projects.
Okay, last one for this section. How do you approach project management in electrical engineering projects?
Time to show off those organizational and leadership skills. Can you handle timelines, budgets, and stakeholders?
Exactly. Think about a project where you were juggling multiple tasks, managing those deadlines, and communicating effectively with your team and the clients.
Right. Did you use any specific project management tools or methodologies? What were your big wins? What lessons did you learn along the way?
And don't shy away from talking about those challenges you faced.
Oh, absolutely. Did you have to deal with scope creep or unexpected delays? How did you adapt and keep the project moving forward?
Project management skills are a must-have for any engineer, especially as you climb that career ladder. Highlighting these skills can really set you apart.
And guess what? RoleCatcher's AI can help you here, too.
I was just going to say that. Their tools can help you create professional-looking project timelines, track your progress, and even identify potential risks. It's like having a virtual project manager right there in your pocket.
Exactly. We'll delve deeper into those AI features later, but for now.
Let's take a quick break and come back with even more interview questions and expert advice to help you crush that interview.
Sounds good. All right, back to those interview questions. You've got the technical skills, you've got the passion. Now it's time to show them you can handle the human side of engineering.
Because let's face it, engineering's a team sport. This next question really puts that to the test. Describe a situation where you had to work with a difficult team member.
Ooh, we've all been there, right?
Yeah. Yeah.
The key here is to focus on the situation, not on bad-mouthing the other person. What made it difficult? Was it clashing personalities, different working styles, conflicting priorities?
Right. And most importantly, how did you handle it? Did you try to find some common ground? Did you communicate openly and respectfully? Did you seek guidance from a mentor or manager?
Think about a time when you had to take the high road, put the project's success ahead of personal conflicts.
Yeah, interviewers want to see that you can navigate those tricky situations with maturity and professionalism.
Absolutely. Now, here's a question that can make people squirm. Tell me about a time you failed. Nobody likes to admit their failures, but this can actually be a great opportunity to showcase your growth mindset.
Oh, I like that.
Right. Failure happens, it's inevitable, especially in a field as challenging as engineering. What matters is what you learned from it.
Exactly. Did you analyze what went wrong? Did you figure out how to improve? Did you develop new strategies to avoid making the same mistake twice?
Exactly. Choose an example where you can show resilience and a willingness to learn from those missteps.
Maybe you miscalculated a load and tripped a circuit breaker, or underestimated the time for a task and had to scramble to meet a deadline.
It happens. The point is to show that you can turn a negative into a positive learning experience.
And don't be afraid to be a little vulnerable. Sharing your failures in a thoughtful way can actually make you more relatable, more human.
It shows self-awareness. Okay, back to the technical side. Explain the difference between AC and DC current. This is a fundamental concept every electrical engineer needs to know.
Absolutely. You need to be able to explain that difference in terms of current flow, voltage variation, and applications. AC current, or alternating current, reverses direction periodically, while DC current, direct current, flows in one direction only.
Right, think about it. The power outlets in your house use AC, but the batteries in your devices use DC.
Perfect example. Now, if you really want to impress them,
Go a little deeper.
talk about the history. The War of Currents between Thomas Edison and Nikola Tesla. That's a fascinating story that shaped the electrical landscape we know today.
Totally. Okay, let's move on to safety. What is grounding and why is it important? This is all about protecting people and equipment from electrical shocks.
Right. Grounding provides a low-resistance path for current to flow to the earth, just in case there's a fault.
Imagine a situation where the insulation on a wire breaks down and that live wire comes into contact with a metal chassis.
Oh, that's not good.
Not good at all. But if that chassis is grounded, the fault current will safely flow to the earth, and that prevents a dangerous shock hazard.
It's so important. You can explain this using simple terms, like the grounding wire acts like a safety net, redirecting excess current away from people and sensitive equipment.
Exactly. And you could even mention different grounding techniques used in electrical systems like TNS, TT, and IT systems.
Yeah, each system has its own pros and cons depending on the application.
Okay, ready for a problem-solving challenge?
No.
You notice a circuit breaker keeps tripping. How would you troubleshoot this issue? This is a classic scenario that tests your methodical approach.
All right, let's break it down. What are some possible causes for a tripping circuit breaker?
Well, the most common is an overloaded circuit, but it could also be a short circuit or even a faulty appliance.
Right, so how do we isolate the problem? Would you start by checking the load on the circuit?
You could, yeah. Or maybe use a multimeter to test for continuity and voltage. See if you can isolate individual appliances to see if the tripping continues.
Good point. And of course, always emphasize those safety precautions.
Of course. Disconnect the power before working on a circuit. Never work on live circuits unless you're properly trained and equipped.
Safety first.
Yeah.
Okay, now, for one of the fundamental laws of electrical engineering. Explain Ohm's law and its applications. This law describes the relationship between voltage, current, and resistance, and it's essential for understanding how circuits work.
It's the foundation. You'll want to state the law clearly. V equal IR, where V is voltage, I is current, and R is resistance.
Got it. And then give some practical examples of how Ohm's law is used in real-world electrical engineering. Could you calculate the current flowing through a resistor given the voltage and resistance values?
Exactly. Or determine the voltage drop across a component given the current and resistance.
Perfect. You can even talk about the limitations of Ohm's law and situations where it might not apply, like nonlinear circuits.
Good point. Okay, next up. What is the difference between a single-phase and a three-phase power system? This takes us into the world of power systems and their applications.
So single-phase systems use a single alternating current waveform, while three-phase systems use three waveforms that are 120 degrees out of phase with each other.
Right. And you'll want to explain the advantages of three-phase systems. Their ability to deliver more power with less copper wire makes them perfect for high-power applications like motors and industrial equipment.
Yeah, think big factories and heavy machinery. But don't forget to mention the applications of single-phase systems too, like in residential wiring.
Good point. Okay, let's move on to a safety device that's often overlooked. Explain the function of a fuse and how it works. Fuses are crucial for protecting electrical circuits from those dangerous overcurrents.
Think of it like a safety valve for your electrical system.
Exactly. A fuse has that thin wire that melts when the current gets too high, that interrupts the flow of electricity and prevents damage to the circuit.
Like a sacrificial element that protects the rest of the circuit.
Precisely. You could describe different types of fuses too, like fast-acting and slow-blow fuses, and how they're used in different electrical systems.
Yeah, and you can even mention the advantages of fuses over circuit breakers, like they're cheaper and have a faster response time.
Now let's step into the world of transformers. Explain the working principle of a transformer and its applications. Transformers are essential in power systems. They let us step up or step down voltage levels as needed.
They're like the gear shifters of the electrical world.
Great analogy. A transformer uses electromagnetic induction to change the voltage and current levels in an AC circuit.
So you could describe those different types: step-up transformers, step-down transformers, and their roles in power distribution, electronics, all sorts of things.
Absolutely. You could even talk about transformer efficiency and the factors that affect their performance, things like core losses and copper losses.
Okay, let's shift gears to motor control. Describe different methods for controlling the speed of a DC motor. DC motors are everywhere, and controlling their speed is super important for many of their applications.
For sure. You'll want to discuss different techniques like pulse width modulation, PWM, armature voltage control, and field weakening.
Explain the pros and cons of each method and when you'd use them. For instance, PWM is a popular choice because it's efficient and offers really precise control.
Exactly. Now let's tackle a concept that often causes confusion. What is power factor and why is it important? Power factor represents the ratio of real power to apparent power in an AC circuit.
So it's all about how effectively the electrical power is being used.
Right. You want to explain the difference between real power, which does the actual work, and reactive power, which is wasted.
And emphasize why it's so important to maintain a high power factor.
Absolutely. It reduces those energy costs and improves overall system efficiency.
You could even mention techniques for improving power factor, like using capacitors to compensate for that reactive power.
Good idea. Now let's dive into the world of semiconductor devices. Explain the working principle of a diode and its applications. Diodes are essential in so many circuits, making sure current flows in one direction only.
They're like the one-way streets of the electrical world.
I like that. You can describe how a diode is structured, a p-type semiconductor and an n-type semiconductor joined together.
Right, and then explain the concept of forward bias and reverse bias, and how the diode behaves differently in each condition.
Exactly. When a diode is forward biased, current flows easily, but in reverse bias, it blocks the current.
It's like a gate that swings open one way but stays shut the other way.
Perfect analogy. And don't forget to give practical examples of diode applications, things like rectification, voltage regulation, and signal clamping.
All right. Switching gears to digital logic, explain the difference between an AND and an OR gate. In gates and OR gates are the building blocks of digital circuits. They're behind all those complex logic functions.
Absolutely. You can describe the truth tables for both gates, showing how the inputs relate to the outputs. For an AND gate, the output is only high when both inputs are high. For an OR gate, the output is high if either input is high or if both are high.
Right, so it's like for an AND gate, both conditions have to be met. But for an OR gate, only one condition needs to be met.
Exactly. And then you can provide some real-world examples of how these gates are used in digital circuits, in logic operations, decision-making, and control systems.
Okay, now for a component that's everywhere in embedded systems, what is a microcontroller and how does it differ from a microprocessor? Microcontrollers are basically tiny computers on a single chip, while microprocessors are the central processing units, CPUs, of computers.
Right. So explain those key differences. Microcontrollers typically have built-in peripherals, things like memory, timers, and input-output interfaces. That makes them perfect for controlling specific tasks.
Right.
Whereas microprocessors are more general purpose and need external components to make a complete system.
So microcontrollers are like specialized tools for specific jobs, while microprocessors are more like a blank canvas.
A good way to think about it. And provide some examples of microcontroller applications, like in appliances, cars, and industrial automation.
They're everywhere. Okay, let's zoom out a bit and talk about the big picture. What are some of the emerging trends in electrical engineering that excite you? This is your time to show off your passion and your awareness of what's new and exciting. Talk about things like renewable energy integration, smart grid technologies, electric vehicles, the Internet of Things, all that cool stuff.
Exactly. Explain why these trends excite you and how you see yourself contributing to their development.
And get specific. What aspects of those trends really grab your attention? Are you fascinated by the challenges of integrating solar and wind power into the grid? Or are you excited by the potential of using AI to optimize energy consumption in smart buildings?
Great examples. Okay, now let's talk about teamwork. Describe a situation where you had to collaborate with a team to solve a complex electrical engineering problem. Teamwork is crucial in engineering, so interviewers want to see you can work well with others.
Absolutely. Highlight a project where you worked effectively as part of a team, emphasizing those communication, problem-solving, and collaboration skills.
Right. Describe the problem, the roles everyone played, the challenges you faced, and how you all arrived at a solution.
Did you have to brainstorm different approaches, delegate tasks, manage deadlines?
And what about resolving conflicts and building consensus within the team? These are all important aspects of teamwork.
Now let's shift gears to project management. Describe a time when you had to manage a project with tight deadlines. How did you approach that challenge? Project management skills are highly valued, and this question lets you show off your ability to handle complex projects and deliver results.
Choose an example where you delivered a project under pressure. Highlight those organizational, time management, and communication skills.
Right. Explain how you prioritized tasks, managed your time, and kept everyone informed.
Did you break the project down into smaller, more manageable chunks? Did you create a detailed schedule and track your progress? Did you communicate proactively with your team and the client?
And it's okay to acknowledge the challenges you face.
Yeah, maybe you had to work long hours or make tough decisions under pressure.
But focus on how you overcame those obstacles and delivered the project successfully.
Resilience is key. Okay, let's talk safety again. Describe a time when you identified a potential safety hazard in an electrical system. How did you address the situation? This question shows your attention to detail and commitment to safety.
So describe that hazard, how you spotted it, and the steps you took to mitigate the risk.
Was it a loose wire? A faulty component? An inadequate grounding system? How did you analyze the situation and decide what to do?
And emphasize the importance of being proactive about safety and being willing to speak up when you see something that's not right.
Exactly. Did you report it to your supervisor? Did you take immediate action to isolate the hazard and prevent potential accidents?
Safety should always be a top priority. Okay, let's delve into electrical codes and standards. Why is it important to comply with electrical codes and standards in your designs? These codes are essential for ensuring safety and reliability, protecting both people and property.
Absolutely. Explain the role of organizations like the National Electrical Code, NEC, and the International Electrotechnical Commission, IEC, in setting those safety guidelines. They develop and maintain codes and standards that cover everything from residential wiring to those massive industrial power systems.
Right, and highlight the consequences of not complying with these codes. We're talking electrical shocks, fires, equipment damage, even legal penalties in some cases.
It's serious stuff. Okay, time to flex those problem-solving muscles again. You're working on a project and hit an unexpected technical challenge. How do you approach solving the problem? This one tests your critical thinking skills and your ability to adapt.
Love it. Describe those steps you'd take, starting with defining the problem, gathering information, and brainstorming potential solutions.
Would you consult with colleagues? Or search online for similar problems? Would you try to isolate the problem and test different components? Would you experiment with different approaches until you found a solution that worked?
Highlight those analytical skills and your ability to use resources effectively.
Now let's talk about communication. You need to explain a complex electrical engineering concept to a non-technical audience. How would you approach this communication challenge? Being able to communicate effectively is so important in engineering, especially when you're working with clients, stakeholders, or team members from different backgrounds.
It's all about bridging that knowledge gap.
Exactly. Emphasize the importance of using clear and concise language, avoiding jargon, and using analogies or visuals to make the concept easier to grasp.
Give them an example of how you'd explain something like electricity or circuits to someone without a technical background. Could you use a water analogy to explain voltage, current, and resistance? Or maybe a simple diagram to show how electricity flows in a circuit.
Great examples. Okay, let's talk about stress management. Describe a time when you had to work under pressure, juggling tight deadlines and multiple priorities. How did you handle it? This question gives you a chance to show off your resilience and those time management skills.
So describe that high-pressure situation, the challenges you faced, and how you prioritized tasks and managed your time to deliver those results.
Did you create a schedule and stick to it religiously? Did you break down big tasks into smaller, more manageable ones? Did you communicate clearly with your team and the client to manage expectations?
Remember, interviewers want to see that you can handle the demands of a fast-paced work environment and stay calm under pressure.
Absolutely. Okay, let's shift to leadership. Describe a situation where you took initiative and led a team to achieve a goal. This is your chance to showcase those leadership qualities.
Highlight an example where you demonstrated those leadership skills, motivating the team, delegating effectively, and making decisions that led to success.
Describe the goal, the obstacles, and how you guided the team to victory.
Did you communicate the vision clearly? Did you empower your team members? Did you provide support and guidance, but also allow them to take ownership?
Those are all hallmarks of good leadership. Now, let's talk about staying ahead of the curve. How do you stay up to date with the latest advancements and technologies in electrical engineering? Technology is constantly evolving, so interviewers want to see that you're committed to keeping your skills sharp.
This is where you talk about those professional organizations like the IEE, industry publications, online courses, and conferences. These are all valuable resources for staying current.
Right. Highlight specific areas you're interested in and how you plan to expand your knowledge. Are you into renewable energy, power electronics, AI applications in electrical engineering? What are you doing to deepen your expertise?
And don't forget about networking. Conferences and professional organizations are great ways to connect with other folks in your field, learn from their experiences, and hear about new trends.
Now let's talk about your ambitions. Where do you see yourself in 5 years? This is your chance to show your career goals and how you plan to achieve them. Be specific.
Do you see yourself specializing? Do you want to move into a leadership role? What are you doing to develop those skills and gain the experience you need to reach your goals?
Interviewers are looking for people who are driven and ambitious with a clear vision for their future.
All right, let's get practical. You're designing an electrical system for a new building. What are the key things you'd consider? This question tests your understanding of design principles and your ability to think about a project holistically.
So mention things like load calculations, power distribution, safety codes, energy efficiency, and future expansion possibilities. Load calculations tell you the total electrical demand of the building. Power distribution involves designing those wiring and circuit breaker systems that deliver the power.
Right.
Safety codes have to be followed strictly, and you need to know the codes for your area.
Absolutely. And energy efficiency is super important these days. You should be thinking about incorporating energy-saving features like LED lighting and high-efficiency HVAC systems.
And don't forget about future expansion. Buildings often get renovated or expanded, so you need a system that can handle those changes.
Good point. Okay, back to safety. What are some common electrical safety hazards in the workplace, and how can you prevent them? Electrical safety is paramount. Interviewers want to see you understand the risks.
Right. Mention those hazards like electrical shocks, arc flashes, fires, and even explosions. Electrical shocks happen when someone touches a live conductor, while arc flashes are those dangerous electrical explosions that can cause severe burns.
Scary stuff.
Yeah, so describe those safety precautions. Using personal protective equipment, PPE, following lockout-ackout procedures, and doing those regular inspections.
PPE includes things like insulated gloves, safety glasses, and arc-rated clothing.
Right. And lockout-ackout procedures involve de-energizing equipment and using locks and tags to prevent it from being accidentally turned back on. Those regular inspections help you spot and fix potential hazards before they cause an accident.
Now, let's dive into circuit analysis. Explain the difference between Kirchhoff's current law and Kirchhoff's voltage law. These are fundamental laws for analyzing how current and voltage flow in complex circuits.
Kirchhoff's current law says that the total current flowing into a junction must equal the total current flowing out.
Like, imagine a point where 3 wires meet. What goes in must come out.
Exactly. And Kirchhoff's voltage law states that the sum of the voltages around any closed loop in a circuit has to be 0. Picture a simple circuit with a battery and a resistor. The voltage across the battery must equal the voltage drop across the resistor, so the total voltage around that loop is 0.
Right. Explain how those laws are used to analyze circuits and solve for unknown currents and voltages. They're essential tools.
Okay, let's talk about control systems. What is a PID controller and how does it work? PID controllers, or proportional integral derivative controllers, are used all over the place to control processes and keep things running smoothly.
They're like the brains of many automated systems.
Exactly. Explain what each part of the controller does. Proportional, integral, and derivative, and how they contribute to achieving the desired control.
So the proportional term responds to the current error, the integral term considers past errors, and the derivative term anticipates future errors.
Right, and then give examples of how PID controllers are used in various industries like temperature control, motor speed control, and process automation.
For example, you could use a PID controller to keep the temperature in a furnace constant by adjusting the fuel flow based on temperature readings.
Perfect example. Now, let's explore power electronics. Explain how a MOSFET works and its applications. MOSFETs, or metal oxide semiconductor field effect transistors, are used all over in power electronics for switching and amplifying electronic signals.
They're like tiny electrical switches.
Exactly. Describe how a MOSFET is structured and how it controls the flow of current between the source and drain terminals using an electric field at the gate terminal.
And give some examples of where MOSFETs are used, things like switching power supplies, motor drives, and amplifiers.
Switching power supplies use MOSFETs to efficiently convert DC power from one voltage to another.
And motor drives use them to control the speed and torque of motors.
Exactly. Okay, let's get into signal processing. What is a Fourier transform and how is it used in electrical engineering? The Fourier transform is a powerful mathematical tool that lets us analyze signals in the frequency domain. It reveals information that might not be obvious when looking at the signal in the time domain.
It's like breaking down a complex sound into its individual frequencies.
Exactly. Explain how the Fourier transform works by decomposing a signal into its different frequency components. For example, you could say a complex audio signal is like a bunch of sine and cosine waves at different frequencies, each with its own amplitude and phase.
And then give some examples of how the Fourier transform is used, things like signal analysis, filtering, and communication systems.
In signal analysis, you can use the Fourier transform to identify the frequency components of a signal.
Right. And in filtering, you can design filters that remove unwanted frequencies.
And in communication systems, the Fourier transform is used to modulate and demodulate signals, allowing information to be sent over long distances.
Okay, let's talk about being adaptable. What steps would you take to learn a new electrical engineering software or tool? Technology is always changing, so you've got to be adaptable and ready to learn new tools.
Highlight your willingness to learn and your resourcefulness. Mention things like online tutorials, training courses, user manuals, and those helpful online communities.
Those are great resources for getting up to speed on new software.
Absolutely. And don't be afraid to experiment. The best way to learn is by doing, so dive in and work through some tutorials and examples to see how the software works.
Hands-on is the best way to learn. Okay, let's talk about design flaws. You're working on a project and discover a flaw in an electrical system. What would you do? Design flaws are inevitable. The important thing is how you deal with them.
Describe the steps you'd take, starting with verifying the flaw, assessing the impact, and letting the right people know.
So would you try to reproduce the flaw to make sure it's really there?
You could, yeah, and then you'd analyze the potential consequences. Is it a safety issue, a reliability problem? Will it impact performance?
Right, and then you'd need to inform your supervisor, the project manager, or the client about the flaw and your proposed solution.
Transparency is key. Then outline your approach to finding a solution. Would you redesign a component, implement a workaround, consult with an expert?
Maybe you'd research alternative components, modify the existing design, or seek advice from a specialist.
Remember, design flaws happen. It's how you handle them that matters. Being transparent, accountable, and committed to finding the best solution is what counts.
Okay, now for a more personal question. What inspired you to become an electrical engineer? This is your chance to share your passion for the field.
Talk about your interests, your inspirations, your goals. Were you fascinated by electronics as a kid? Did you have a mentor who sparked your interest? Are you driven by solving real-world problems with your technical skill?
This is where you let your genuine enthusiasm for electrical engineering shine through.
Authenticity is key. Share your story in an engaging way so the interviewers can see your passion.
All right, back to safety. What are the key provisions of NFPA 70E and why are they important for workplace safety? NFPA 70E is all about protecting workers from electrical hazards. It covers everything from risk assessments to PPE.
Mention those key provisions, things like risk assessments, electrical safety programs, lockout procedures, and the use of PPE. Risk assessments are all about identifying potential hazards. Electrical safety programs establish safe working procedures.
And lockout tagout ensures that equipment is de-energized before anyone works on it.
Right. And PPE protects workers from shocks, arc flashes, and other dangers. Emphasize that complying with these regulations is absolutely critical for preventing injuries and fatalities.
Safety should never be taken lightly. Now, let's talk about power quality. What are harmonics and how do they affect electrical systems? Harmonics are multiples of the fundamental frequency of an AC waveform, and they can distort the waveform, causing problems.
Explain how they're generated. Harmonics can come from nonlinear loads, like variable frequency drives, computers, and electronic ballasts in fluorescent lighting. These loads draw current in a way that introduces those harmonic frequencies into the system.
Right, and describe the problems they can cause. Harmonics can overheat transformers, motors, and wiring. They can also interfere with sensitive electronic equipment and trip those protected devices.
Exactly. And then mention ways to mitigate harmonic distortion, things like using filters and harmonic mitigation transformers. Filters can block specific harmonic frequencies, and harmonic mitigation transformers can protect sensitive equipment from harmonic currents.
All right, let's dive into solar energy. Describe the different types of solar photovoltaic PV systems and their applications. Solar PV is becoming more and more popular as a clean and sustainable energy source.
Talk about different PV system configurations like grid-tied systems, off-grid systems, and hybrid systems. Grid-tied systems are connected to the utility grid, and they can actually sell excess power back to the grid.
So you can actually make money.
You can. Off-grid systems are independent and need battery storage.
Right, for when the sun's not shining.
Exactly. And then there are hybrid systems, which combine both features.
The best of both worlds.
Exactly. Explain the pros and cons of each and when you'd use them. Grid-tied is usually the most cost-effective option, while off-grid provides energy independence but requires a good amount of battery storage. Hybrid systems are flexible, but can be more complex and expensive to set up.
Okay, let's talk about energy storage. What are some of those emerging energy storage technologies, and how can they benefit the grid? Energy storage is becoming a key part of the shift to a more sustainable energy future.
Mention things like lithium-ion batteries, flow batteries, and pumped hydro storage. Lithium-ion batteries are used a lot in electric vehicles and are gaining popularity for grid-scale storage. Flow batteries are good for large-scale applications, and pumped hydro storage is a more mature technology that uses the potential energy of water stored uphill.
Wow, so many options. Explain how energy storage can help with integrating renewable energy sources, improving grid reliability, and lowering energy costs.
Renewables like solar and wind power are intermittent, meaning they're not always available. Energy storage helps provide a consistent power supply even when the sun isn't shining or the wind isn't blowing.
Right. It's like a backup system for those times when renewable energy generation dips.
Exactly. It can also smooth out fluctuations in demand, reducing the need for those inefficient and polluting peaking power plants.
All right, let's talk about the future of the grid. What are smart grids, and how can they improve efficiency and reliability? Smart grids use all sorts of fancy technology like sensors, communication networks, and data analytics to optimize the grid.
Explain how smart grids can balance loads better, reduce energy losses, and make it easier to integrate renewable energy sources.
So smart meters can provide real-time data on energy consumption, allowing utilities to match supply and demand more effectively.
Exactly. Sensors can monitor grid conditions, allowing for proactive maintenance and faster fault detection.
And communication networks enable two-way communication between utilities and consumers, allowing for demand response programs and other innovative grid management approaches.
Now let's talk about power system protection. Explain the role of relays in protecting systems from faults. Relays are those critical protective devices that detect abnormalities and act fast to isolate faults and protect equipment.
They're like the safety guards of the electrical grid.
Describe the different types of relays. Overcurrent relays, undervoltage relays, and differential relays.
Overcurrent relays trip when the current gets too high, protecting against overloads and short circuits.
Undervoltage relays trip when the voltage drops too low, protecting against voltage sags.
And differential relays compare the currents going in and out of protected zone, tripping if there's an imbalance, which signals a fault.
Right. Explain how relays work and why they're so important for safety and reliability. Relays use electromagnetic or electronic sensing to detect those abnormal conditions.
So they're constantly monitoring, looking for trouble.
Exactly. And when a fault is detected, the relay sends a signal to a circuit breaker, which interrupts the current flow and isolates the fault.
Preventing damage and keeping things running smoothly.
Okay, let's talk about electrical drawings. What are the key elements of an electrical schematic diagram, and how do you interpret them? Schematic diagrams use symbols to represent components and their connections. They're like a visual language for electrical circuits.
So mention those key elements, like the symbols for resistors, capacitors, inductors, switches, and power sources.
Resistors are those zigzag lines, capacitors are parallel lines, inductors are coils, switches are open and closed contacts, and power sources have their own symbols.
Right, like batteries and those AC source symbol.
Exactly. Explain how to interpret those connections between components and use the schematic to understand how the circuit works. Schematic diagrams show you the flow of current and the logic of the circuit.
You can trace the path of the electricity and see how the components interact.
Okay, now for some hands-on electrical testing. Describe the steps you'd take to test the continuity of a circuit. Continuity testing checks if there's a complete path for current to flow, making sure there are no breaks.
It's like checking if the electrical road is clear.
Explain the steps, like using a multimeter to measure the resistance between 2 points in the circuit. You set the multimeter to the resistance or continuity mode, and then touch the probes to those 2 points. If there's a complete path, the multimeter will show low resistance, usually close to 0 ohms. If there's a break, it'll show high resistance or an open circuit.
And of course, always emphasize those safety precautions.
Always. Disconnect the power before testing. Never test on a live circuit. You could damage the multimeter or even get a shock.
Safety first. All right, let's compare motors. Explain the difference between a synchronous motor and an asynchronous motor. Both are types of AC motors, but they operate differently.
Synchronous motors rotate at a speed synchronized with the frequency of the AC power, while asynchronous motors, also called induction motors, rotate slightly slower than the synchronous speed.
So synchronous motors are locked in step with the power supply frequency, while asynchronous motors have a bit of a lag.
Exactly. Describe how each type works and where they're used. Synchronous motors are used when precise speed control is needed, like in clocks and timers.
Right, where accuracy is key.
And asynchronous motors are super common in industrial applications like pumps, fans, and conveyor belts.
They're the workhorses of the industrial world. Now let's talk.
And asynchronous motors are super common in industrial applications like pumps, fans, and conveyor belts.
They're the workhorses of the industrial world. Now let's talk about power conversion. Explain how an inverter works and its applications. Inverters are those handy devices that turn DC power into AC power, letting us use things like batteries and solar panels to power regular AC appliances.
Right. Describe those different types of inverters. Pulse width modulation, PWM inverters, and square wave inverters.
PWM inverters can adjust both the frequency and voltage of the output, while square wave inverters have a fixed frequency and voltage.
Exactly. And then explain where inverters are used. Renewable energy systems, uninterruptible power supplies, UPS, and motor drives.
In renewable energy systems, inverters take the DC power from solar panels and wind turbines and turn it into AC power that can be used in homes and businesses.
And UPS systems use inverters to provide backup power when the grid goes down.
Keeping those essential devices running.
And in motor drives, inverters control the speed and torque of AC motors.
Okay, let's talk about power system stability. What is power system stability and why is it important? Power system stability is all about the ability of a power system to stay balanced and keep running smoothly, even when there are disturbances, like faults or changes in load.
Right, it's about resilience. Explain those different types of stability. Transient stability, dynamic stability, and steady-state stability.
Transient stability is the ability to stay synchronized after a big disturbance, like a fault. Dynamic stability is the ability to dampen those oscillations that can happen after disturbance, and steady-state stability means operating within acceptable voltage and frequency limits under normal conditions.
Exactly. And then talk about the things that can affect stability. Load changes, generator outages, transmission line faults, and even problems with those control systems.
Right, and those techniques used to improve stability, like automatic voltage regulators, AVRs, and power system stabilizers, PSS.
AVRs keep the voltage stable, and PSSs help dampen those oscillations.
Okay, let's talk about high voltage safety. Describe how you'd safely work with a high voltage power supply. High voltage equipment can be extremely dangerous, so it's crucial to follow strict safety procedures.
Absolutely. Emphasize the importance of following procedures, using PPE, and ensuring proper grounding.
Before you even touch that power supply, read the manufacturer's instructions and those safety guidelines carefully.
Right. And then describe those steps. Checking the voltage settings, connecting the load, and monitoring the output.
Double-check those voltage settings and make sure the load is connected properly and can handle the voltage and current.
And never, ever work on high voltage equipment alone.
Always have someone else there who can help if something goes wrong.
Now let's talk about AC voltage measurements. What's the difference between RMS voltage and peak voltage? AC voltage goes up and down like a wave, it's sinusoidal.
RMS voltage, or root mean square voltage, is the effective value of an AC voltage. Peak voltage is the highest point of that wave.
Explain how RMS voltage is calculated and why it's the one we use to represent the effective heating value of an AC voltage.
RMS voltage considers the entire waveform, not just the peak, so it gives you a better idea of the overall energy.
Right. For example, a 120V RMS AC voltage will produce the same amount of heat in a resistor as a 120V DC voltage.
Okay, let's talk about circuit configurations. Explain the difference between a series circuit and a parallel circuit. Series and parallel circuits are the two basic ways to connect electrical components.
In a series circuit, the components are connected end to end, so the same current flows through each one.
Like a single path for the electricity to follow.
Right. And in a parallel circuit, the components are connected across the same 2 points, so they all have the same voltage across them.
Like multiple paths for the electricity to take.
Describe those characteristics of each type, like how the current and voltage relate.
In a series circuit, the total resistance is just the sum of all the individual resistances, and the current is the same everywhere.
But in a parallel circuit, the total resistance is actually less than the smallest individual resistance, and the voltage is the same across each component.
And give them some examples of series and parallel circuits in everyday life.
Think of those old-school Christmas lights. That's a series circuit. If one bulb goes out, the whole string goes dark.
But the wiring in your house is a parallel circuit.
Right. If one light bulb burns out, the others stay on.
Okay, let's dive into electromagnetic theory. Explain Faraday's law of electromagnetic induction. Faraday's law is fundamental to electromagnetism. It describes how a changing magnetic field can create an electromotive force, or EMF, in a conductor.
It's the principle behind generators. Describe how Faraday's law is used in all sorts of devices, like generators, transformers, and inductors.
Generators use it to create electricity, transformers use it to step voltage up or down, and inductors use it to store energy in a magnetic field.
Now let's talk troubleshooting. You're working on a circuit, and a component isn't working right. What do? Troubleshooting is a key skill for any electrical engineer. This question is about showing your methodical approach to finding and fixing problems.
So start with the basics. Check the power supply. Make sure there aren't any loose connections.
Right, make sure the circuit is getting power and that everything's connected properly.
Then, grab your multimeter and measure the voltage and current at different points in the circuit.
That'll help you isolate the problem and see if the component is getting the right voltage and current.
If you need to, isolate the component and test it on its own.
That way, you can tell if the component itself is bad or if the problem's somewhere else in the circuit.
Okay, let's talk about a safety device that can be a real lifesaver. Explain how a ground fault circuit interrupter, GFCI, works. GFCIs are designed to protect against shocks by detecting those dangerous ground faults.
They're essential in wet areas like bathrooms and kitchens.
Describe how a GFCI constantly monitors the current flowing through those hot and neutral wires, and it trips the circuit if it senses an imbalance.
It's like a super sensitive safety switch.
So if some current is leaking to ground, maybe through a person or a faulty appliance, the GFCI will shut things down super fast.
Preventing a potentially fatal shock. Okay, let's explore power distribution. Describe the different types of power transformers used in electrical substations. Power transformers are those big guys in power systems that step voltage up or down for efficient transmission and distribution.
They're the heavy lifters of the power grid.
Right. Talk about those different types. Step-up transformers, step-down transformers, and auto transformers.
Step-up transformers increase voltage, step-down transformers decrease it, and auto transformers can do either, depending on how they're wired.
And explain what they do in power distribution.
Step-up transformers are used at power plants to boost the voltage for long-distance transmission. Step-down transformers are at substations, bringing the voltage down to levels that are safe for homes and businesses.
And auto transformers are used for things like voltage regulation and impedance matching.
Now let's talk about the challenges of renewable energy. What are the challenges and opportunities of integrating large-scale renewables into the grid? Renewable energy sources like solar and wind power are great, but they can be a bit unpredictable.
Right. Talk about those challenges. Intermittency, grid stability, and the need for energy storage.
Intermittency means the sun isn't always shining and the wind isn't always blowing.
And the fluctuating nature of renewables can make it tricky to keep the grid stable.
And then there's the need for energy storage to smooth things out and provide power even when those renewable sources aren't available.
But don't forget the opportunities. Renewables mean reduced carbon emissions, greater energy independence, and even economic benefits.
They're better for the planet, reduce our reliance on fossil fuels, and can create jobs and boost the economy.
Okay, let's dive into AC motor control. Explain the different ways to control the speed of an AC induction motor. AC induction motors are everywhere in industry, and controlling their speed is crucial for many processes.
We need to be able to make them go faster or slower as needed.
You can control the speed by changing the frequency, voltage, or resistance in the motor circuit. The most common way is variable frequency drive, VFD control, which adjusts the frequency of the power, giving you precise control over a wide speed range.
VFDs are like the DJs of the motor world.
Talk about different control methods like VFDs and rotor resistance control.
VFDs convert the fixed frequency AC power from the grid to variable frequency power for the motor.
And rotor resistance control involves adding resistance to the rotor circuit to slow the motor down.
Explain the pros and cons of each method.
VFDs offer great control, efficiency, and less wear and tear on the motor, but they can be pricey.
Right, and rotor resistance control is simpler and cheaper, but less efficient and offers less control.
Okay, let's compare electrical codes. What are the main differences between the National Electrical Code, NEC, and the International Electrotechnical Commission, IEC, standards? Both the NEC and IEC are widely used electrical codes, but there are some key differences.
The NEC is mostly used in the US, while the IEC standards are international.
And the NEC is more about specific requirements, while the IEC focuses more on performance goals.
Highlight those differences in scope, terminology, and requirement.
The NEC covers more areas than the IEC, including residential, commercial, and industrial installations.
Right, and the words they use can be different, and the specific rules for things like wiring and equipment can vary.
Okay, let's talk about picking the right motor. You're on a project and need to choose a motor for a specific job. What would you consider? Choosing the right motor is important for efficiency and reliability.
So many factors to think about. Talk about things like load requirements, speed and torque characteristics, operating environment, efficiency, and cost.
The load will determine how powerful the motor needs to be.
Right, it needs enough muscle to do the job.
And the motor speed and torque characteristics have to match the needs of the application.
And you have to think about where the motor will be used. The environment can affect the type of enclosure and insulation you need.
Efficiency is important for saving energy and money.
Of course. But cost is always a factor too, right?
Right, you have to balance cost with all those other factors to make sure the motor meets the needs of the project.
Now, back to power quality. What are voltage sags and swells, and how can they affect equipment? Voltage sags and swells are those brief dips and spikes in voltage that can mess with sensitive electronics.
Sags are short drops in voltage, and swells are short rises.
They're like hiccups and surges in the power.
Sags are often caused by starting big motors or heavy loads.
Like when your lights dim momentarily when the refrigerator kicks on.
Right. And swells can be caused by switching off large loads or by faults in the system.
Explain the problems sags and swells can cause.
Sags can make sensitive equipment malfunction or shut down, and swells can damage things or shorten their lifespan.
So what can you do about them?
You can use things like voltage regulators, surge protectors, and those trusty uninterruptible power supplies, UPS, to protect your equipment.
All right, let's talk about oscilloscopes. Describe the steps for safely using an oscilloscope to measure an AC voltage waveform. Oscilloscopes are those cool tools that let you see and analyze electrical signals, but you have to use them carefully.
Safety first. Emphasize those precautions, like connecting the ground lead first and setting the voltage range correctly.
The ground lead protects you from shocks if there's a problem with the circuit.
And setting the voltage range higher than the expected voltage protects the oscilloscope from damage.
So walk through the steps. Connecting the oscilloscope, setting the time base and voltage scale, and reading the waveform.
First, connect the probe to the point in the circuit where you want to measure.
Then set the time base so you can see the waveform clearly.
And adjust the voltage scale to make sure the waveform fits nicely on the screen.
Oscilloscopes give you a ton of information about the signal, like its amplitude, frequency, and shape. You can learn a lot about a circuit by looking at its waveforms.
Okay, let's talk about impedance. Explain the concept of impedance and how it's different from resistance. Both impedance and resistance measure how much a circuit opposes the flow of current, but they're different for AC and DC.
Impedance is the total opposition to AC current, while resistance is just the opposition to DC current.
Impedance includes both resistance and reactance, which is the opposition from inductors and capacitors, while resistance is just pure resistance.
Resistance fights both AC and DC, but reactance only affects AC.
Right. Explain how impedance is calculated, using those complex numbers that take into account both the magnitude and phase.
And talk about how impedance affects the way current flows and the voltage drops in an AC circuit.
Okay, let's talk about resonance. Explain what resonance is in electrical circuits. Resonance happens when the inductive reactance and capacitive reactance cancel each other out.
It's like those swings on a playground. If you push at just the right frequency, the swing goes higher and higher.
Describe what makes resonant circuits special, like their ability to store energy and their use in filters, oscillators, and tuning circuits.
Resonant circuits can store energy in their inductors and capacitors, and at resonance, they let maximum current flow.
They're used in filters to pick out specific frequencies, in oscillators to create signals at a specific frequency, and in tuning circuits to select a frequency from a range of frequencies.
Okay, let's talk about rectification. Explain how a rectifier works and where it's used. Rectifiers are essential because they change AC power to DC power.
Lots of electronic devices need DC power, but the power from the wall is AC.
Describe those different types of rectifiers, like half-wave and full-wave rectifiers.
Half-wave rectifiers use one diode to convert only half of the AC wave to DC, while full-wave rectifiers use multiple diodes to convert both halves, resulting in a smoother DC output.
So full-wave rectification gives you a more consistent DC voltage.
Exactly. Talk about where rectifiers are used, like in power supplies and battery chargers.
Power supplies use rectifiers to convert the AC power from the wall to DC power for electronic gadgets.
And battery chargers use them to convert AC to DC for charging those batteries.
Okay, let's talk about a serious electrical hazard. What is arc flash, and how can you prevent it? Arc flash is a dangerous electrical explosion that happens when a large current flows through the air.
It's like a mini lightning bolt, and it can cause serious burns. It can be caused by short circuits, ground faults, or other electrical problems.
Scary stuff. Describe what causes arc flash and those important safety precautions, like wearing arc-rated PPE and following lockout-tagout procedures.
Always de-energize equipment before working on it. Wear the proper protective gear, and follow those lockout-tagout procedures.
Safety should always be the top priority. Now let's talk about different types of electrical diagrams. What are the different types of electrical diagrams and what do they tell you? Electrical diagrams are like maps of electrical systems, used to communicate designs, troubleshoot problems, and help with installation and maintenance.
Talk about different types: schematic diagrams, wiring diagrams, and block diagrams.
Schematic diagrams show those electrical connections, using symbols to represent components.
Wiring diagrams show you how the wires are actually laid out and connected.
And block diagrams give you that high-level overview of the system, showing the major components and how they're connected.
Each type of diagram serves a different purpose.
Schematic diagrams for design and analysis, wiring diagrams for installation and troubleshooting, and block diagrams for understanding the system as a whole.
Okay, back to grounding. Explain power system grounding. Power system grounding connects electrical systems to the earth to provide a safe path for those fault currents.
It's all about keeping things safe.
Talk about those different grounding systems. Solidly grounded and ungrounded systems.
Solidly grounded systems are directly connected to earth ground, while ungrounded systems aren't.
The purpose of grounding is safety. It provides that low impedance path for fault currents to flow to the earth,
which helps limit the voltage that could build up on surfaces and cause shocks.
Now let's explore solar thermal energy. Describe those different types of solar thermal systems and what they're used for. Solar thermal systems capture sunlight to heat water or air for all sorts of uses,
like water heating, space heating, and industrial processes.
Talk about different solar thermal systems like flat plate collectors, evacuated tube collectors, and parabolic trough collectors.
Flat plate collectors are simple and affordable, while evacuated tube collectors are more efficient but pricier.
And parabolic trough collectors are used for those high temperature applications like generating electricity.
Explain how those systems work.
They typically use a fluid, like water or glycol, to absorb heat from the sun and move it to a storage tank or heat exchanger.
Then that heated fluid can be used for hot water, space heating, or industrial processes.
Okay, let's talk variable frequency drives. What is a variable frequency drive, VFD, and how does it work? VFDs are those electronic devices that control the speed of AC motors by changing the frequency and voltage.
They're like the speed dials for motors.
Explain why VFDs are so useful.
They save energy, give you precise motor control, and reduce wear and tear on equipment.
VFDs can fine-tune the motor speed to perfectly match the load, saving energy and reducing wear.
They're used all over the place in HVAC systems, pumping systems, material handling, all sorts of things.
Well, that wraps up our deep dive into electrical engineering. We've covered a lot of ground today, from those fundamental concepts to the latest trends and technologies.
We've explored circuit analysis, power systems, motor control, renewable energy, and so much more.
And remember, you don't have to be an expert in everything.
Right. What matters is having a strong foundation and being able to apply your knowledge to those real-world problems.
And that's where RoleCatcher's AI tools can really make a difference.
Their AI can analyze job descriptions, pinpoint those key skills employers are looking for, and even help you tailor your resume and cover letter.
It's like having a personal career coach in your pocket.
So use those resources, prepare thoroughly, and go into that interview with confidence. Show them your passion for electrical engineering, ask thoughtful questions, and engage in a conversation. The best interviews are those where everyone learns something.
Relax, be yourself, and let your knowledge and enthusiasm shine through. Best of luck with your interview. We know you'll do great.